A typical support team handles 5,000 tickets a day. Half are routine questions, password resets, accounts, checks, shipping status, and etc. And each ticket costs $4 to $8 operational overhead, then handled manually. An AI-assisted flow changes that math. The system retrieves documentation and generates a cited answer in under 2 seconds, dropping the cost to 30 to 80 cents per ticket. The savings do not come from the cutting stuff here, they come from automating repetitive work, so your team can focus on complex cases that need the human judgment. By the end of this course, you will build that system, a support copilot that ingests documents, retrieves context, generates answers, and passes quality to the security checks before you deploy it to somewhere. Today, we lay the foundation, the business case, the architecture, and the project skeleton that makes everything else possible. Let us start with the real numbers from the companies already running it at scale. In early 2025, the intercom company reported that customers using Fin AI resolved 45% of conversation without human handoff, cutting average resolution time from 11 hours to under 2 hours for automated queries. Costs per resolved conversation dropped roughly 60% for participating companies. Speed and cost savings compound here. Faster answers reduce queue load, improve customer satisfaction, and free up senior agents for the work that truly requires expertise. Klarna saw similar results in 2024. Their AI assistant handled 2/3 of customer service chats, doing the work of 700 full-time agents with a sustained 25% reduction in support cost year over year. The break-even point arrives quickly because the cost structure flips. You pay per API call instead of the human time, and the system scales without adding headcount. Those results come from specific architecture called retrieval augmented generation, which is RAG. Let us walk through what that means. Retrieval augmented generation is a pipeline that grounds language model answers in real documents. It has 3 stages: ingestion, retrieval, and generation. Ingestion splits documents into chunks, converts each chunk into embeddings, and stores those embeddings in Postgres with pgvector or any other vector database. An embedding is a list of numbers that represents the meaning of the text. Think of embeddings as the coordinates in meaning space. Reset password and forgot password land near each other because they describe the same problem, even though the words are different. And that is why semantic search works. Retrieval happens at query time. A user types a question, we convert that question into an embedding using the same model, then we search the vector database for the chunks those embeddings are closest to the query embedding. Postgres pgvector uses cosine distance to rank the results, and this is not a keyword matching, it is the semantic similarity. So the system finds relevant answer even then the wording is different. The third stage is generation, where the language model uses the retrieved chunks to answer the question. So our final result, basically. Generation takes retrieved chunks and the original query, builds a prompt that says, answer this question using only the following documents, and sends the prompt to a language model like GPT-4, for example. The model generates a response grounded in the retrieved context and can cite with the chunks it used. This drastically reduces hallucination because the model is not inventing facts, it is just summarizing the real documentation. So if we imagine that user asks, how do I update my billing address, the system searches for the chunk about account settings, billings, and profile updates, for example, which is again not the keyword matching but semantic similarity, as I mentioned above. And then it retrieves the top 5 most relevant paragraphs. The language model reads those paragraphs and generates the answer. Go to the settings, then billing, and then click edit address. It cites the documentation chunk it used, so the user can verify the answer. So the lesson is that retrieval quality gates everything downstream. If the search returns irrelevant chunks, the language model cannot generate a useful answer, and no matter how powerful the model is. That's the three stages pipeline is what we are going to build in this course. But first we need to answer a common question. Do we need an agent or the similar pipeline is enough? An agent is a system where a language model decides which tools to call and when. It might search the knowledge base, then call an API to check account status, then search again based on what it found. Agents iterate until the problem is solved. They are powerful for research tasks, multi-step reasoning, or the workflows where the next action depends on prior results. A pipeline executes fixed stages in order. Every query goes through retrieval, then generation without any branching. Pipelines are simpler, faster, and cheaper because there is no decision-making overhead here in between. You know exactly what will run and how much it costs. For support automation, we start with pipeline because most queries follow predictable patterns. A user asks a question, we retrieve relevant docs, we generate an answer. That flow does not need the dynamic planning. If later we discover that some tickets require checking live account data, for example, we can add agentic behavior. What we have to remember is that agents add complexity. So, we are building a pipeline. Now let us map that pipeline to the architecture and the project structure you will work with. Our project mirrors the three-stage pipeline in its folder structure. The project layout is ingestion for chunking and embedding, retrieval for vector search, and generation for language model calls, plus cache, eval, security, and tests. We split this into separate packages because each stage has different infrastructure needs and scaling characteristics. Separating these stages into packages means you can test, scale, and debug each one independently, which is the best pattern for you to use in production. Right now, most of these folders contain only placeholder files. Episode 1 is about the skeleton and the local runtime. We will fill in ingestion, retrieval, and generation in the next few episodes and add evaluation and security checks before we deploy. The infrastructure runs in a Docker Compose locally. 3 services. Postgres with the pgvector extension for storing chunks and embeddings, Redis for caching, and the Fast API application. All 3 run in shared Docker network, so the API container can reach Postgres and Redis by service names. Compose also defines health checks, so Postgres and Redis are ready before the API starts. That is pretty much the architecture we have. Now let's see what we actually built in this first episode. First, we have to build and start the stack. With Docker Compose app build, we compose and build API image, pulling Postgres and Redis, and starting all these services. Now we have to check the service status with Docker Compose PS. This is the very common command. Postgres and Redis both show healthy in this status column, and that means that the health checks have passed. Finally, I verify that API responds to the health endpoint. The response is simple, like the status OK, and it confirms that the fast API process is now also in the container. And that is the pretty much entire scope of the episode 1. We have a project structure that mirrors the React pipeline, a local runtime where the Postgres, Redis, and the API run on the Docker network, and a smoke test that proves the infrastructure is healthy. In the next episode, we will build the ingestion layer, reading documents, chunking, generating embeddings, and storing them in the Postgres with pgvector. So by the end of this course, you will have a working support copilot. Imagine a user types a question, something like, how do I reset my password? And the system retrieves relevant documentation from your knowledge base, generates a cited answer in under 2 seconds, and displays which documents it used. We will run automated quality tests for retrieval precision, answer faithfulness, and security checks for prompt injection and data leakage before we deploy. It is small but a production-ready pipeline with observability, evaluation, and hardening building. If you found this video helpful, learned something new, or discovered ways to simplify your workflow, boost your productivity, or even save money, please subscribe my channel and hit the like, because it really helps me to grow and keep digging to discover new things and continue creating more content like this. Also, leave a comment below with your thoughts, questions and experiences. My goal is for us to learn, grow and build real AI expertise together, and your feedback is an important part of that. Thanks for watching and see you in the next videos. Life is dead so now.